Mark. All right, so for this first one, you're measuring temperature of a substance, and the definition for temperature is a measure of the average kinetic energy. And so if kinetic energy is equal to 1/2 mass velocity squared, you're not really measuring the mass. So what you're doing is you're measuring the velocity. And so really, I mean, you could make this simple and just say you're measuring the speed of the molecules. Potential energy. So this is energy that can do, and the kinetic energy is doing. Examples of the can do stuff. I saw a lot of gas in a car. I saw a pine cone about to fall. And then what I thought of, especially after this last week, was a phone. You know what I'm talking about with that? A phone about to fall from 16,000 feet.
Oh, was it from the plane?
So that American Airlines flight that was over Portland, they were at 16,000 feet, and the emergency door blew out. So the door landed in a teacher in Beaverton's yard. And then the next day, somebody just found a cell phone in the grass on like next to a sidewalk, just sitting there. It was an iPhone. They didn't say which one it was, but regardless, this iPhone was just sitting there, and it was on, and they picked it up, and it was in airplane mode, and it was open to the application for checking your baggage. So the person was sitting there looking at their phone, the door blew out, and the decompression pulled the phone out of their hands and it threw it out. So if that's not an Apple ad, like in the next week, I'd be shocked. Like, our phone fell 16,000 feet. No problem.
They got it back.
It's going to the FAA, and then I'm sure it'll get to them at some point. So the kinetic energy, we could say that phone that is falling from that 16,000 feet, or that pine cone that is actually falling now. Those would be good examples of kinetic energy. So the Fahrenheit 0 is equivalent to no liquefying ice with salt. I don't like to use the word melt when I'm talking about this particular instance, because melt always connotates heat, and there's no heat going on here. All right, so you hit a tree. Where'd all that kinetic energy go? What are your give me some places it went?
To the tree.
Well, what do you mean to the tree?
So,
But it's kinetic energy, right?
so movement, so if it hits, the tree can move.
Okay, so the tree moves, but it's a tree, so it probably didn't move very much. But what about the tree moved? Is that it?
You could, depending on the it could get torn up from its roots. It could even just like have some blemishes and damage done to it.
Yeah, bark got tossed, right? The tree itself shook, right? So pine cones might have fallen. That took force to make those pine cones come down. Branch might have get torn off. A section of the tree got torn apart. If the tree itself got split in some way, I mean, that's an extent. If you split wood, you realize how hard that is, especially with green wood, living wood. So all of that takes energy. And then the other things are that I didn't see a lot of are some heat will be generated for sure. And then the other one is sound. So if you're near this car crash, you will hear that car crash. So how did you hear the car crash? What had to happen for you to hear it? What's the nature of hearing?
Sound waves.
So what does that mean when we say sound waves? It's kind of misleading. Like I'm talking to you right now, and how are you hearing that? Like, what's the physical process that allows you to hear?
Vibration, there you go.
But what's doing the vibrating?
Air.
Air. That's the only thing that's in your ear, right? So my vocal cords are vibrating air particles. Those vibrated air particles are leaving and they're making their way to you. And then you're interpreting those vibrating air particles with all the different parts of your inner ear. So I'm hearing this car crash that happened with this tree. And the reason I'm hearing it is because that car hit that tree and caused those air particles to vibrate a lot. And then those particles came all the way to me. Depending on, you know, what the wind conditions are, you might be able to hear that for like a mile if it's calm. So all of those air particles got moved. So that all that kinetic energy got put into a whole bunch of different spots. What are you doing? Weird. Okay, so recommended daily allowance is 2,000-ish calories. So we're looking at 200,000 lowercase calories, which is going to be equal to 2,000. You could write K calories with a lowercase c, or you could write 2,000 capital C AL. And then it's 4.183. Is that right? I don't think that's right. 4.64.
Is it not 184?
Yeah, it's down to 184.
Is it 184? All right. 184 joules is equal to 1 calorie. And so then I've got these calories. So the cals cancel out, and then multiply this by joules. So it's like 8 something on the right. 8.184. 4.81. So 8.368 times 10 to the 6th joules. And then we what are we doing here? Yeah, I guess that's right. I suppose that you could say that's 4 sig figs. I didn't get exactly what I was looking for. Oh, wait, maybe one person gave me exactly what I was looking for this non-specific example. Something like how hard it is to heat something. That's it. So it's really easy to heat a piece of aluminum foil. It's really hard to heat an orange because of the specific heats of those two objects are so different. All right, calculate the amount of heat needed to raise the temperature of water, 250 grams. Okay, so what we need to know here is that the specific heat of water is 1 calorie per gram degree C. And since I'm looking for heat, I'm going to start with 1 calorie gram degree C. That way I've got the calorie unit in the numerator. I'll put 250 grams in the numerator so I can cancel out the grams in the denominator. And this is change in temperature. So 98 minus 2. So this is 96 degrees Celsius here. Cancel that out. So that 96 goes up top so I can get the Celsius unit to cancel at the bottom. So it's just 96 times 250. So 24,000 calories. I should have put in a decimal place here, but there's only one significant figure there. So technically your answer would need to be 20,000 calories.
Doesn't feel right.
Doesn't feel right. Yeah, but that's the way it is. If you add 350 calories of energy to 1.2 kilograms of copper, the initial temperature is, what's the final temperature? Okay, so we're looking for a temperature thing here. We're going to have to look up copper's specific heat. I think it's 0.92 calories. No, there's a 0 in there. Grams degree C. All right, so I need a temperature. So I'm going to use 1 gram degrees C divided by 0.092 calories. Why did I write this upside down?
That's interesting.
So I can get the temperature unit on the top, and so then I'll put 1200 grams. I'll just convert that, and the grams disappears. And then what do we add? 350 calories. So the calories cancel out, and then this will be 350 divided by 0.092 divided by 1200. Divided or multiplied. Seem right. Oh yeah. I got 3.17 degrees C. Okay. So this temperature change, this is my temperature change. This is how much the temperature is going to change. But I started at 19, so I'm going to have to add that 19 degrees to it. So I get 22.17 degrees C, and we've got 2 sig figs, so then my answer will be 22 degrees C. So this last one, this is pretty much what you guys did in lab, right? So the first thing that we need to realize is we need to determine how much heat that the water is going to gain. And so we've got how much water? 300 grams of water and 15 degrees starting in front of. Okay, so 45. All right, so I need to know the heat. So I'm going to start off with 1 calorie gram degree C so I can get a heat unit. Then I've got 300 grams to cancel out the gram value. And then I've got a 45 degree temperature change to cancel out the degree C. And then this is 300 times 45. So this is 13,500 calories of energy went into the water. So this is Q of the H2O. And so my Q of the, what do we put in here? Lead equals negative 13,500 calories. Okay. I need a temperature change. So then I'll use lead specific heat. I'll write it upside down. So 1 gram degrees C, and that's 0.038 calories. All right. So then I had 80 grams of lead. So the gram unit cancels out. And I had negative 13,500 calories. So the calorie unit cancels out. It's going to give me a negative, so negative 13,500 divided by 80 divided by 1. So this is negative 4,440. So we got 3 sig figs, 2 sig figs. Okay. And so that's degrees C. So this is the change in the temperature. And so then our change in temp is equal to temperature final minus temperature initial. And what's the other little tricky thing that you have to realize in this problem? So this is my change in temp. I'm looking for the initial temp. So what's the final temp? What's the thing I need to realize? Like, it doesn't give me the final temperature in here directly, only indirectly. It's got to be the same as the water, right? They're both the lead sitting in the water. So whatever the final temperature of the water is, that will also be the final temperature of the lead. So the final temperature of the water was 60 degrees C, and my so that's minus temperature initial equals negative 4440 degrees C. And so if I solve for this temperature initial, it negative gives me a positive. So subtract. So 4,500 degrees C. Is that right? Adding 60 to that. Yeah. Okay. So that lead was really hot. That's letting you know two things. Is that a big deal for water to go from 15 degrees Celsius to 60 degrees Celsius? Well, I mean, for us, like, if I gave you 15-degree water, like in a glass or a cup, would that be hot or cold? 15 degrees C.
With one, a little less than.
Less than room temp, right? Little, not cold, but cool. And then what about 60 degrees C?
It's like 140, something like that.
So like not,
Almost scalded.
I wouldn't say scalding, not Starbucks hot or McDonald's hot, less than that. Those get up to like 160 Fahrenheit. That's why people keep suing them, although whatever. So this like cool water went up to like drinkable tea. That was it. That's all that happened. But for me to do that with a piece of metal, what was the initial temperature of the metal? Ridiculous, right? And so what's that based on? The fact that the leads, mostly it's based on the fact that the lead specific heat is so much smaller than the water specific heat. Plus, we also had a significant difference in the mass, is 380, between 300 and 80. So heating water with metal, not a great idea. The metal itself isn't going to hold very much heat unless it's a really big piece of metal. Okay, that's it.